Hello, hello. Hi. Hello. I'm just waiting for everyone to show up, maybe. And I'm just going to send out a link to everyone who wants to be here. AP Chemistry. Link to join me, if I could spell. Okay. Hello. Hi there, Mr. Frank L. All right, we got Adam. All right, people have joined us. All right. About chat. Just waiting for some people with some questions, and we can rock and roll. Some people say they were there first. Well, so all about this KSP stuff. Now, I am assuming, all right, that you guys have watched the videos, and I can, as a surgeon, just help you out. So my first question, can you explain letter D on the Equilibrium 5 worksheet? Okay, certainly can do that. So let's go somewhere. Let me just pull up that sheet. And for those other questions, you're just going to have to wait. All right, so it's 5A, right? No, it's 5. I believe this is it. And hopefully you can still see that. And here we go. So in D here. The question is, at 25 degrees Celsius, the concentration of magnesium in a saturated solution of magnesium fluoride is 1.17 times 10 to the 3 molar. Is the dissolving in the water endo or exothermic process? Give an explanation to the support of your conclusion. Okay, well, party people, the problem here is, I got my bamboo upside down, that's the problem. The problem here is, and if you're checking this out and you can't see the screen, change your view to 720. Hopefully that helps. Okay, I did some tests today, so if you're on like the lowest rate, I'm kind of should be broadcasting a pretty high quality. All right, but hey, who knows? All right, so the question is, all right, then letter D is a kind of gets you sometimes, but this is what we've been working on in terms of how energy affects, well, how energy affects pushing a reaction forward or reverse by changing the K, or in this case, the Ksp. So if we notice, the problem initially was at 18 degrees Celsius. That's the key to the problem. And we learned, and should have learned, that all the problems that we just did in this question here, great question, and a very typical type of question, hint, 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 is that 18 degrees Celsius, all right, that's where this Ksp kind of resided. Remember, the temperature and the equilibrium constants, all right, are temperature sensitive. So everything's going to be at the same temperature. So you notice all your questions were at the same temperature. All right, all at the same temperature except for letter D. Letter D was different. They did what? They increased the temperature. So by increasing the temperature, what did we learn last week? Hopefully, that if we increase the temperature, we're going to favor the endothermic direction. Okay, that's important. And if we decrease the temperature, we would favor the exo. So the question is, where is the heat in this reaction? Is it on this side or this side? So back to the problem. I know I don't have the work here. Back to the problem. What do we know? Well, at 18 degrees Celsius, the problem that we just did, okay, they used the word saturated, and saturated is what we talked about in class. That screams to you equilibrium, as these problems are. And we notice that the mg plus 2 is equal to 1.21 times 10 to the negative 3. Okay, and that was the first question. Okay, where, remember the first question, they wanted the Ksp and they gave you the concentrations of them, so, and you squared them. So yeah, so you found well, they just gave you the question, they gave you the mg plus 2 concentration to be this. So that was actually just given to you in the first question. So now they're saying at 27, the concentration is now 1.71 times 10 to the negative 3. So what just happened for the mg plus 2? What just happened was that this concentration of the magnesium ion dropped. It went down. Okay, now think about, we had what? Magnesium fluoride. Let's write the reaction. Magnesium fluoride, F2, breaking apart. This is how we write it for Ksp reactions. Broke apart to Mg plus 2 aqueous and 2 fluoride ions aqueous. So what happened was, at a higher temperature, at 27, so when temperature increased, all of a sudden the amount of magnesium dropped. Can you see from going from these two values, this got smaller. So at a higher temperature, the amount of magnesium got smaller, which means what? Which means somehow the Ksp or the Kq, okay, shifted in a way to push the reaction this way. So the equilibrium changed in a way so that it favored, okay, more of the solid or less of the what? Ions. So if we had this U tube again, and here's my K, well, it moved this way, and it moved this way even more, okay? It favors the reaction to move to the left, like Beyonce. And what that tells us, and again, I don't know what people missed in class, but what I tried to teach you was that that favors the endothermic way. So if we're losing magnesium plus 2, if it's dropping, so will F2 because Le Chatelier's principle is saying there's a quote shift. And now I don't like that word because when it comes to temperature, we're actually changing KSP. Our KSP is actually moving this way, right? Because equilibrium is temperature sensitive. That's one of the major things we learned. Okay, and KSP is a type. So basically, the reaction is moving more spontaneously to favor more reactants, which of course is this solid, and less of the products, which is the ions. So we would say that the heat is on the what? Heat is on the product side, and therefore the dissolving of MgF2 in water is exothermic because I've got heat here. And why does that work? Well, if I have heat as a product, that means I'm starting with the solid, I'm going down as the ions, and here's our reaction pathway. We start high, we end low. The difference is that delta H is negative because the energy is going to be released. And we always know when heat is written on the product side, it's released. All right. So that screams to me it's an exothermic forward reaction because by increasing the temperature, we watched Mg plus 2 drop. And again, if you're still not with me on that, we like to draw these kind of diagrams. Stress, response. And what we just saw was that and again, kind of weird because we're looking at what happened, but we saw that the magnesium was dropping. Okay, when we increase the temperature, okay, the reaction wants to lower the temperature. Okay, so we increase the temperature from what? 18 to 27. And the reaction wants to drop the temperature. So it wants to use up the heat. Now, how did I know it went to the left? Because the magnesium was going down. When I compared the concentrations, magnesium was going down, which means it was moving toward the reactants. We all know it's because the KQ became even smaller. Okay? And that's the answer. So knowing that it shifted to the left by the equilibrium changing because the temperature dropped, we knew it shifted to the left because the magnesium dropped. And because we know, and this is key, anytime you increase the temperature, you favor the endothermic way. So this way, going in reverse, had to be the endothermic way. And what do we know about the endothermic way? You need heat to go in the reverse. So the endothermic way was the reverse reaction. The forward reaction, of course, is exo. What makes this very confusing is they said, is the dissolving endo or exo? And clearly the dissolving is in the forward, okay, going in the forward because the heat's written on the product side in the forward is exo. Okay, I'm going to check to see if I did okay with that. All right, so I got a bunch of questions after that. Frank, are we all good now? Letter D okay for you now? Give me some sign that that may have worked for you. All right, you bet, Frank. All right, so now next question I have is Emma in the house. Can you explain what you know about potatoes? Okay, that's kind of weird. No, can you explain what you know you're supposed to cross out when you get into the situation where you need to use the quadratic? Okay, the quadratic. All right, well, the quadratic formula, okay, that is something we're never going to see. So let me ask you if I got your question. Can you explain what you know, what you're supposed to cross out when you get the situation when you need to use the quadratic? Well, we never use the quadratic formula, never. So we always basically get away from the catastrophe. All right. For instance, let me give you an idea here. Looking at B here, not this one. This is 5A or 5. This is 5. So if you're looking at 5, okay, and a question like this, um, let me just set this up. So the catastrophe, which of course you missed Friday, not your fault, is an idea where if we do not approximate away a part of these equilibrium problems, we're going to have some issues and we're going to have to need the quadratic formula. So given letter B, and there's a lot going on for letter B of this ditto, but we had magnesium, F2, and it's breaking apart into the magnesium plus 2. And I just want to set this up for you. Hopefully you can see what I'm talking about, because again, the keys are hard to look at individually. I know I did this, but so this said calculate the equilibrium concentration of Mg plus 2. Okay, so they want to know this. And of course, we use our ICE table. This is initial, this is the change, and this is at equilibrium. So what we're looking for is what is the magnesium ion concentration at equilibrium. Okay, given this set of circumstances. Now we can't measure the solid, so we're not going to go here. Now initially, what do we have? Well, if you read the question, it says calculate the equilibrium concentration of magnesium in a liter of saturated, the key saturated. That word saturated right here is telling you we're at equilibrium at 18, to which 1 mole has been added. So if it's saturated, we're going to assume it all dissolved. It dissolves, it dissolves completely. I can read. Okay, so what do I know? I know that I have a 0.1 mole of solids been added. Okay, and that solid of Kf is a common ion. Kf breaks apart into K plus and F minus. So what I would do is I'm really adding a molar solution. So essentially I have 0.100 molar here. Now it's going to be on top of what we have initially, because they gave us in the first part of the question a solution of MgSO4. So calculate the equilibrium in a liter of saturated MgF2. So that's essentially what we just did for A. Okay, you just did A, and if you're looking at your work, we found that the Mg plus 2 was 1.21 times 10 to the negative 3, and that the F negative was 2.42 times 10 to the negative 3. Okay, now this is going to be, this is what we have already in a saturated solution. They said we have this solution. We figured out in A what those values were. Okay, and you solve for KSP. Okay, I'm not going to go through that unless you want me to, but, and so we already have these initial concentrations, and then we added a common ion. Kf breaks apart to K plus and F negative. Now K plus isn't involved anywhere in this in these equilibrium, so we're not going to use it, but F is. So essentially, adding a 0.1 mole of Kf, we're adding a 0.1 mole molar solution because it's dissolved by a liter, right? Moles over liter, and I got to add that. Okay. Now, what's my change? Well, as this is going to be losing something, and this is going to be losing 2x. And you may say, well, why am I going to lose something? Well, we're going to have extra amount of stuff here. Okay, so we know that there's going to be a shift this way somewhat, right? This was the amount of stuff we figured out at equilibrium, and now we're adding a bunch of more F negative. So the reaction is going to shift by Le Chatelier's principle. Okay, remember stress, response. Okay, the stress is we're increasing F negative by adding Kf. The response is to lower F negative. So this reaction is going to become more spontaneous in the reverse. Okay, so that's why it's going to go to the left. We're going to lose. Now, why twice as much? Because of this 2. It's, remember, don't forget the stoichiometry. Okay. Now, what's the end product here? Well, normally we just kind of put these things together. Okay, so what we're going to have, party people, we're going to have, all right, 1.21 times 10 to the negative 3 minus x. It's going to lose something. Okay. Now, since they're after this, this is exactly what they're after. I care about this x. We want to know how much this is going to lose as it goes to the left a little bit. Now, over here, okay, we got some stuff going on here. Um, we've got this 0.1000 molar, okay, plus the 2.42 times 10 to the negative 3 minus the 2x. And there's where we're going to have some issues, okay? And this is where we're going to approximate, because if I want to find my KSP, okay, or in this case, they're looking for this concentration, I'm going to take my KSP value, which we found to be, remember, KSP is equal to the concentration of magnesium times the concentration of F negative to the second power. So I know my KSP. We've solved that previously as 7.09 times 10 to the negative 9 to equilibrium. And now I'm going to times it by this number. So I'm equal to this times this. Okay, well, if you do that, okay, you're going to have positive 4x positive. So when you multiply these numbers together, you will get a positive 2x squared here. And you will eventually have, by the distributive property, something else with an x and then a raw number. You'll have a quadratic, and you'll have to solve. We never solve quadratics in this course. You don't have the time. But interesting enough, in chemistry, most often we're dealing with such very, very small equilibrium constants, we do not have to. So party people, what we approximate away is this negative 2x. Now we could keep this number if we wanted to, but this number still is so gosh darn big compared to this, I could approximate this away as well. So remember, why are we minusing 2x? Because we're going this way. Why can we approximate? Well, think with me. If KSP is small, whoa, that's really small. What does our YouTube look like? Well, it looks like we're just a lot more what? Reactants are favored. It's almost impossible to have a Q less than this K. Okay, so we were at this position of Q equals K. This is where we were in the problem. By adding more F negative, we created a Q that went now way over here. So the reaction was going backwards. That's why we did that. Now the question is, how much backwards does it go? Well, it didn't go forward that much, right? At equilibrium, this very little goes forward. Remember, it's products over reactants. So this small number being products over reactants, okay, means that we have barely any products to begin with. So when we forced it backwards, what we're going to do is force it back to this position, and this amount of 2x going back is going to be tiny because we barely went forward in the beginning. So we're going to get rid of this. Now, if you kept this in the problem, it wouldn't change anything. But these numbers are so small compared to this number, we approximate it away. And then, of course, I can put this number here. All right. And then this number goes here. And it becomes an easy problem. Okay, easy problem to solve. Even if it was a squared or a cubed, you can work with it, but a quadratic, we don't have to. The idea is it barely went forward to begin with. So then we forced it backwards, it barely went back. Now I'm drawing the Q way out here. Q became bigger than K, but still it's not going very much in the reverse because it barely goes forward. And that's the key there, Emma, is that we approximate away one of these x's that doesn't matter. See, we're after this value. We want to know what mg is. Okay, so what we do is we solve for x by plugging the values in, and then we know this minus x as the key shows you. Okay, it's going to be a small value. This barely goes forward. Okay, I'm going to check to see if I handle that enough. I may have overtaught that, but I'm tall. Okay, let's see what we got here, party people. All right, so Adam, I answered your question. Come on, Emma, give it back to me here, buddy. Did I answer your question? I would open up the audio, but it doesn't work so well. All right, cool beans. If beans are chilled. All right, so Adam doesn't have a question. I'm assuming I'm speaking fine enough and there's no echo tonight. Frank has another question, and Aiden is doing chemistry thinking. All right. Frank, you're up because no one else has any questions, so type away. No cathedrals today. Good. 5A and Part D. All right, 5A, Part D. Yes, I can do that. So we're gonna do D on 5A. Just give me a second, pull that up. And let's go File, New on Background. And I'm just gonna pull this up. Shared. Grodsky B. Desktop. That didn't work. Grodsky B. And I'll pull that up. Dropbox. AP Chem. SkyDrive. Booyah. AP Bio Chem. Third quarter. And you wanted Equilibrium 5A. All right. Equilibrium 5A. I guess I should have had that open previously, but hey, I'm tall. I'm not sure if you guys can see that new worksheet, so please respond if you can't. Can you see that new worksheet I just posted up there? Can you see the new one I just posted? No. Okay, give me a second. Let me change this. I gotta do something here. Add a new remote local here. And I want window and select the window. Give me a second here, party people. You want yeah, that's it. I think it's 5A. Yes. Okay. No, that's not it. Give me a second. Hello. Sorry. So you lost the audio? I'm going to have to go over that again. Hold on. So stay with me. I'm going to redo that. All right. Sorry, I didn't know I lost audio. Okay. Sorry to stress you out. Check, check, check. We have that one. Okay. Sorry about that. So I'm going to walk you through that again. My bad. So I'm assuming you can hear me now. Don't know why that didn't work. Okay. So it's hard. I don't hear from you except when I check. So no, it's not going to work. Okay. So I did all of that, and I mean, no one could listen to me. So uh, which one is this one? Okay. Everyone can hear me now? Just going to check to make sure, not to stress anyone out. That was a waste of time. Take the moon, take the sun. All right. Can you hear me now? Christmas, a lot of talking going on. All right. All right. So let me go over 5AD. Okay. For whatever reason, that template doesn't have sound. So let me just go back and do that again. I'm all good if you are. All right. So rock on. All right. I'm going to clean this up. Get rid of all of this. This template's working, so I don't know why. I'm going to have to give me a second. Check 1, 2. Okay. Now we have. Can everyone hear me on this one? I'm assuming yes. I'm going to check one more time because now it seems like I have audio for this where I didn't have it before. Okay. Going back. Okay. I'm going to do that one more time. La la la. Boy, this is going to be fun. Good times. At least I practiced. All right. Maybe this will make more sense now that you have some sound. All right. And I don't hear any. Okay. I'm working on this, guys. Okay. So let me explain what this was about. All right. Now that I'm all done this before, I can do this. So what we had, party people, is we had a beaker. And in this beaker, there was 3 little pigs. No, there was strontium sulfate, which was very soluble, and there was strontium fluoride, all very soluble. And initially, okay, we had 0.02 moles of F negative. Now they're all in 1 liter, so you can see that that's going to give me a 0.02 molar solution of F2 ions total. And then the strontium ions, they said there was 0.1. And that was moles over liter, but same idea. Okay, so that was dissolved in a beaker. Now what we're going to do is we're going to add some known amount of strontium nitrate. And who cares? It's soluble, so what we're really adding to this is strontium plus 2 ions. The nitrate's in there too, but it's a spectator. So what I'm after here is who's going to precipitate first. Now I wrote them like Kardashian weddings, but they're not really together. Okay, they do separate into their ions. So the question is, who is going to precipitate first? Okay, well, if we know the KSP, which we do, let's do the strontium first. And this is going to be the strontium ion concentration, plus 2, times the sulfate, negative 2. Okay, well, party people, this concentration right here is 0.10. The KSP we know. Okay, we got that, and that's actually up on the first part. So we know this guy, and we know this, and we're going to solve for the concentration that the strontium has to be if it is saturated, okay, if it's at equilibrium. And this is going to tell me the value of what this has to be in order for the Q to equal K. Okay, so remember the first part in C says I'm slowly adding to already a saturated solution, okay, which means it's at equilibrium. All right, so when we solve for this strontium, we get 7.6 times 10 to the negative 6. And again, what really was this? This was exactly, this is the KSP of strontium nitrate. No, I'm sorry, strontium sulfate. You get the idea. Strontium plus 2, good enough. And this is the solid, and this is the ions, it breaking apart. And this is where the Q equals the KSP. So knowing the equilibrium position and knowing how much of the sulfate ion, I can figure out the concentration of the strontium so that Q equals K. That's my position. And we do the same thing for the next one. KSP is equal to the strontium ion. They both have strontium ions. And then we have the F negative. Now this is squared because there's two F's in this stoichiometric problem. And of course we have the KSP and we have the F negative. They told us that, which in this case it is 0.02. 0.02 molar. And so what we're going to do is we're going to solve for the strontium. Again, what does this mean? Well, we have this U-tube diagram. This guy's got a KSP2. And this is the solid, and these are the ions. And this is the F negative ion and the strontium ion. Collectively give us a position where Q equals KSP. So this would be the value that strontium would have to be, knowing the concentration of fluoride, for us to be in a solution where Q equals K. Okay, so that's what we're solving for. And when you solve for that, okay, you get 1.9 times 1.975 times 10 to the negative 6. So those are the concentrations of my two different ions, okay, based upon their two different KSPs and based upon their two concentrations there. I'm just going to check to make sure you can still hear me, okay? So you can still hear me? I feel like just checking. Nobody's there. Nobody's home. Okay, Aiden, thank you, bud. RJ in the house. Sorry, yep, okay. I got it. We're good. So back to reality here. Now, here's the key now. We had these concentrations. This, of course, is equal to the F negative ion, okay, when Q equals K, and this is equal to the strontium. This is equal to the strontium ion when Q equals K for its salt. So those are the two values. They have to be, okay, given these concentrations of the other ions. Now, what does this mean? Well, I kept adding strontium ions. We want to know who's going to precipitate first. Again, in order for answer D, I have to answer C1 and C2, so sorry. Now, so to answer this, okay, well, when is the strontium ion concentration? When we're pouring extra strontium ions in. And we're putting strontium ions in. If we're going to add strontium ions, we want to know, okay, when eventually, and I'll make this different color, when I add too much, and now what? My Q is greater than K. and it'll start to precipitate. So, which one precipitates first? Well, as I keep adding strontium and strontium concentration in here increases, when will it hit the magic number, which is when they equal Q and everything beyond that? If you look carefully, okay, which one's the smaller number? Okay, well, this one's the smaller number. So you're going to hit this number before you this. So we're going to add strontium ions till we're going to hit this number first, which means for this guy, it's going to make the Q equals K and then make it go above that. It's the first one to drive it past the Q. At 1 point times 10 negative 6 strontium ions, that's not enough to make this KSP be bigger than its Q. Right now, it's below Q. In fact, right now, I should say that both of these reactions are starting below. They're starting the scenario with Q is less than K for both of them. Both of them Q is less than K in this position and in this position. And we're going to keep increasing strontium until, if you follow my arrow, it equals Q. Who's going to equal Q first? This one. And then, I'm sorry, the fluoride ion one. So this one's going to equal Q first and go beyond, right? These numbers right here are the values of the strontium ion in this solution where the Q equals K for both of them. And this one gets hit first because we're starting from some low number and we're increasing until we get here. This one is going to be hit first. And it's this one is where Q equals K first. And then as you keep adding anything beyond this number, Q is greater than K, and it's going to go in reverse and precipitation will occur. So we figured out that that precipitates first. Okay, we're moving on to something. Now, the next part of this question says, as more strontium nitrate is added to the mixture, a second precipitate begins to form. Okay, well, I'm going to get rid of some of this. As I can see, I have bad planning, but good posture. Okay, so what we have, party people, is we know that when the second precipitate forms, okay, now well, the first precipitate is what? Strontium fluoride. It has a lower requirement for strontium ions before Q equals K, and everything beyond this number as we keep adding will make Q bigger than K, and then it'll start precipitating as it moves in the reverse. So we know that. But when the second precipitate forms, that must mean that we've reached this number, 7.6 times 10 to the negative 6 for the strontium. So they want to know at the stage when the when this, just as a second precipitate forms, which is screaming to you when we've reached this concentration for the strontium ion, which is what we have right here, okay, what percent of the anion of the first precipitate? Now, anion is a fancy word, pinky up, fancy word, okay, for, I just realized you can't see me now. I put my pinkies up if you can imagine. Where the anion is a fancy word for the F negative ion. So what percent, okay, remains in solution? Now, why remain in solution? Well, think with me, party people. This one hits Q first. And as we add more strontium, the Q becomes greater than K, and the reaction goes in the reverse, which means we start to use up some of this guy as the reaction goes in the reverse. How much is left? Well, we know the KSP, and we're going to use this reaction. So it's going to, it should just be strontium, my bad, is equal to the strontium plus 2 F negative, okay, and of course that's squared. And what we're going to do is we're going to solve for how much of this is left, knowing that this value has reached 7.6, and of course we need the KSP of strontium fluoride. So we have this value, and we have this value, and then we solve for x, which will be x squared. You'll have to do the square root, and you'll get your x. And of course our x is equal to 1 times 10 to the negative 2. So I solve for it. Now, it was 0.02, but it went forward as we increased the amount of what? As we increased the amount of strontium beyond the Q formula, we just pushed this value way up here, and now it's going to go in the reverse and take some of the F negative away from it. And we just figured out when we get to this position, this is how much is left. So percentages part over total, how much do we have? 0.02 times 100, and that's 50%. Or as we say in Riverhead, 50%. Okay, hopefully you can still hear me. I don't have to do that one more time. Hopefully that helped. Okay, let's go see if you can hear me still, and if that helped. Ooh, you said unfortunately. The KSP of your brain, assuming you have a lot of ions in your brain, probably very soluble. So your KSP is going to be very big. Adam, you said unfortunately. Why? Oh, I know why you can't hear me. Can you hear me now? Can you hear me? You can hear you. Okay. When's the test? I'm spooked now. Well, tomorrow's test is a practice. Okay. So for those that are on, I'm going to sit you down. You're going to practice it. I'm going to grade it, give it back to you. And then Tuesday it'll be a real test. So, yep. I may not put that in, haha, but tomorrow is going to be, I'm going to go over some questions and then give you a 20-minute practice problem based on these kind of things we've done here. Now, these are the most challenging, the ones we just talked about. Okay, so you're going to get to practice on it, and if you could see a lot from these kind of questions, you'll be in good shape. So I'll grade it, email it to you, scan it, email it to you in that order, and then have another practice for homework, and you should be in good shape. What else? No, it won't count, Carolyn. Practice, practice, practice. Tuesday will. Tuesday you'll get one live, but you're going to have tomorrow for practice and then something else for homework, which is also another practice. Okay. Hopefully you went through my videos and you give me some good questions. Frank, I don't know, dude. We'll see. Let's wait and see, Frank. If we do better on the practice test, can the real one use it? Maybe, maybe. You know what? I'll do better at 2. Sure, why not? Whatever you want to do. The Q for my brain would be smaller than the K, favoring the proxy. Yeah, maybe. I don't know. Yes, Tuesday will be an AP question. That's for sure, Emma. They're all AP questions. Everything you've seen from these worksheets are all past AP questions. Yep. Now I picked, of course, 5 and 5A are the most challenging, I think. So sorry for doing about 20 minutes of no audio. All right. Anything else I can do for you? Now Tuesday is also going to be the thermo question too. So make sure you go over your delta G formula with equilibrium. Virtual high five. Here we go. Yes. All right. It's weird if I had 3 hands coming up right now, but that wouldn't be working out. Tomorrow is a practice question in class, so it's not a test. Did I miss any questions? Carolyn, you got a question for me, kid? Scrolling up. RJ, any questions? Adam, any questions? Yeah, Emma, yes, that's the equation with Lynn. You will definitely see a question tomorrow. I mean, not tomorrow, Tuesday, because you're going to have a 2-question one. But you'll definitely see a Lynn there. Meaning of life? My gosh. I would say the sp3 hybridization of water that allows for it to be a very good solvent, the universal solvent. But then again, I would think also that the cellular membrane, its ability to, keep life-sustaining reactions in is also something important for life. That's the best I can do for now, for life. Hopefully you're spontaneous, Josie. Can I go over something we need to know for tomorrow? Well, I will definitely think, let's see here. Which problems are we going to do for tomorrow? Well, you're going to definitely see an equilibrium problem in KSP, and you're going to have to know when Q is bigger than K. So if you took out, equilibrium 5, okay, letter C, if you have that out, okay, um, that is a very typical question, except in B, there was stuff dissolved already. For the most part, you're going to start with no ions. So I would say 5 is a very good example of what you possibly could see. Because you're going to have to do um, some dilution, MV equals MV, all right? And when you're pouring 2 liquids together, you're going to have to do that. You're also going to have to solve for Q and compare it to KSP. So definitely, question 4 and 5. Specifically, do you want to see something? But if you're looking at the equilibrium 5 worksheet, you're going to pour 2 solutions together. You're going to have to find the new molarity using the dilution formula. You're going to have to use those concentrations to get Q. You're going to compare Q to KSP. And then knowing where you are on that U-tube, is it going to go forward or backwards? If Q is greater, then it goes back this way. And if Q is smaller, it's here and it goes forward, So those are the things. I would say in KSP B, you're not going to have any extra, those initial things will be 0. So that worksheet was a little more challenging. Also D with the temperature part was too. So tomorrow's KSP problems will be a lot more straightforward than these. However, there will be a piece to the KSP problems tomorrow where you'll have to know which salt precipitates first. So that's something to keep an eye on too. Certainly I could go through a problem there, but I feel like I've done that on the video. And I can't show you the real problem. That's what practice is about. Now, it doesn't count tomorrow. Unless you do better than the other test, maybe. We'll see. You give us the test key. When to use MV as MV? When you pour 2 solutions together. Okay, that's what I did in class Friday. It's the lecture that was posted for you, the first one you should have watched. And that's where I poured 2 solutions, and therefore the molarity of each of them changed, because if you had, let's say, 50 milliliters of one solution and 50 milliliters of another, and then you pour them together, now the new volume is 100 milliliters, and you're going to have to solve for the new molarity. And that's what you did for question 4 on the worksheet that we did together, and question C on equilibrium 5. So that's an important thing. We do that with acid and bases too. Anytime you pour 2 solutions together, the molarities of what you're measuring change to the new volume. Emily, keep an eye on. Sure. Oh, it's getting strange. All right. If there is anything else, I'm going to call it a night. Those are 2 good questions. And thanks you for coming on. And I hope I helped in some way. Just waiting for any other things you may want to pop up. Do you understand, Emma, about MV and MV equals MV? I'm just reading the comments. All right, thanks. And Carolyn, we good? Audio was better. And you were able to see. Yeah, you guys are hysterical. Okay. I'm going to call it a night, guys. See you tomorrow. Rock on.